I'm able to see it versus waiting to ask, hey, is there any questions? And that works too. That works too.
Okay.
You just don't have to wait till the end to ask me a question. If you ask a question during the lesson, I will stop and address the question asked. Okay,
Okay.
let me see. Yeah, I'm trying to organize myself here. And how do I get out of here? Uh, yeah, I had a meeting. Then I had a meeting after the meeting. Then I had calls and stuff. So I usually take some time to mentally prepare for a class. And let's just say I am here. So yeah, it's all good. Anyway, this is where I left.
Okay.
So this is where I stopped on Tuesday, right, with the people that showed up. So let me go ahead and erase this so I can start from scratch. Funny enough, for my class this morning, this is what I taught. I just taught at a very different level because the different chemistries cover the same content just at different levels. Okay, so prior to this section here, we're talking about there were three main models of the atom we're talking about. Actually, four. If you include Bohr's model, that would be four. So we talked about Dalton's model, and he talked about the atom being round, and he implied there was nothing inside the atom when he said the atom was indivisible. And then we had J.J. Thomson, whom I like to call J.J., like I know him. And he talked about the atom being round. Okay, imagine that was round. And he described the plum pudding model. In the pudding model, that would be like a circular muffin, blueberry muffin, where your blueberries were electrons. And then the interior of the whole atom is essentially positive. He described a neutral atom. After him, we had his ex-best friend, Rutherford. Sometimes called Rutherford, depending on how you want to pronounce it. I pronounce it like an African. If I don't have a proper pronunciation, I just pronounce everything that
I've
way.
just heard Rutherford, so it's like,
Yeah, I've heard Rutherford. I've heard all that. I'm like, well, yeah, these are not
but
American
then
people.
yeah, but at the same time though, it's like David Bowie or Bowie or Bowie. I've
Right.
heard like
I'm like, these are not
50,000 versions.
people with English backgrounds. They're usually European, like German, whatever. So I don't know the true pronunciation. So when everything else fails, I pronounce the vowels like they were African vowels. So with him, he talks about the nuclear model. And his objective was to help his mentor and friend J.J. Thomson. He ends up proving that J.J. Thomson's model is not correct based on the experiments that he performed. He is credited for the gold leaf experiment, where he proved that there was a nucleus in the atom. The nucleus was small, very hard, very dense. It was positive. And then you had electrons occupying the available empty space in the atom. Then after him, we move on to the most popular model. Da da da. That will be I was about to say quantum mechanical model. No, that's not. Bohr's model. Bohr's model is the planetary model. This is the model we talk about with Jimmy Neutron and Big Bang Theory. This is the one that you see
Oh
on
yeah,
TV. Yeah, the popular one. Everybody knows about that one.
like the
Yes, this is
planted.
the planetary one. What do you say?
Oh no, I was just trying to describe it. I get what you mean.
Yeah, so the location of it was built after the planetary model where the sun would pretty much be the nucleus, and then you had electrons in the place of planets orbiting around the nucleus. In his model, Bohr describes electrons as having a specified orbit and implying that their path around the nucleus was predictable. Okay? And then, of course, we now have the quantum mechanical model, which I like to call QM squared because it's cool. And the quantum mechanical model is very difficult to describe because um, it's difficult to describe. In the place of orbits, we have orbitals. The orbits are 2D, the orbitals are 3D. The orbit is a path, a described path, a specific path. The orbital is a region. So we're talking about a volume, a space, right? So things get complicated here. Everybody agrees the nucleus is the center, the nucleus is positive. But instead of having a specific shape of the orbit, and by the way, the orbits are all round. With the orbitals, we have various shapes. So today we're going to be talking about the different shapes. So we don't just have a round shape, which we will call a sphere. We have other shapes for the orbitals.
Like
Okay.
ovular or like just in general like
It's
weird.
round. We have round figure eight, clover leaf, and then the flower. I
Oh,
like
okay,
to
okay.
call it the flower. Right. So it's not it's not an oval or cylindrical or anything like that.
Oh.
So with this one here, we have you can draw circles, but they're really actually spheres versus circles, and then you have figure eights, and then you have cloverleaf. So when you if you're able to find the structure of this online, it looks like balloon animals shoved inside a circle. Not really that simple, but you have bubbles versus concentric circles like we had with Bohr's model. So this one here, I should say, it's complicated. A lot of scientists don't even dare attempt to draw the whole quantum mechanical model. When people try to draw it, they always put a disclaimer out there. All we're showing is a small part of it, so you can see, and then imagine, fill in the gaps with with your imagination. Okay, so
I
back
guess
to
that's
this.
why 3D modeling might help with that kind of stuff.
I tried one time, but it's complicated. Now let me tell you what I did one time. No, that was this year. Let me tell you something, okay? I told my friend, I think we need to all agree from January to March was a different year. And then the rest of this is a different year because there are things that happened in February of this year that I ascribed to last year because, you know what I'm saying? Once Corona
Yeah.
came in, I feel like we set a whole different timeline. But anyway, this spring, around February, I went to a workshop where they had, oh, what's that thing called? They had virtual reality goggles. And okay, this is how I'm very nerdy. You had through the goggles, there was an opportunity for you to go to this, not really the not the nucleus, but to go inside the atom of the goggles. And then you got to select different energy level and they show the energy level around you. So, I mean it's all in your eyes, right? So you can kind of go in there and then poke the spherical region, and then they showed you other ones. I couldn't figure out how to work it out long enough. Then the session was over and somebody else had to come in. So I was like, oh man. But somebody actually used 3D simulation to simulate the spherical orbitals around the nucleus. So you could see with 3D and you were able to kind of go through one level to another all the way to the nucleus. And I poked the nucleus. That was pretty cool.
Was it like I don't know how to describe this besides was it like uh something that was like specifically made for that like event or did
I
they
don't know.
buy
I want to
like
say it was a software made for those goggles, but then those goggles we were able to find them online. They were not cheap. They were not cheap at all. So
oh,
I
okay,
think
so it's
it
like an
was
Oculus Rift or like a
right one of those things. I didn't even know it existed, but yeah. So the software though, he was trying to convince us this would be good for you guys to have on campus for students to learn. And I was like, wait a minute.
yeah.
You're saying they will come and look at this and then they're like, yeah, and then leave it on the desk for them to look at and then, come back and pick up later. I'm like, pick up one. I was
Is
like,
that a
yeah,
headset?
yeah.
Yeah,
They were,
there
they
were
were trying
oh,
to sell it. What
oh,
they
okay.
say?
Yeah, well even then that's gonna be kind of
It would be
interesting 'cause
pricey. Yeah, it would be
yeah,
pricey.
that and like not to get off subject too much, but the Oculus Rift I've heard. it's joined with Facebook. They own it. So now they're starting to ask people to we're required to have a Facebook account in order to do
Oh,
that.
I see what
Like
you're
getting
saying.
like they might start adding more to it, like subscriptions or like I don't know. So it's like later on.
Interesting. Yeah, that's interesting. So yeah, I mean, of course, if it was on campus, maybe we'll have like our own whatever for the school, and then we'll log into that. And all students will have to do at that point will be to maybe to describe what they see, draw it out, and then answer questions. But I was like, yeah, I don't think we are ready for that yet. Yeah, so the quantum mechanical model is, yeah, give me just a moment. Oh, today is just one of those days. Yeah. It's a model that uses four quantum numbers to describe the electrons. So the biggest thing we're doing here with the first three quantum numbers is trying to describe the orbital of the electron. So the orbital is that 3D region around the nucleus where the electron is assumed to be. The electron is in the orbital. So the idea is the three quantum numbers describe the orbit. And once we know the orbit's location, we technically know the electron location. Okay, so bottom line, location of the orbit equal location of the electron. So when the electron is inside the atom, the electron doesn't exist there just naked. It usually exists inside a portal, or I guess you can say a capsule, and that capsule is the orbit. So the orbit is essentially the home of the electron. So if you're trying to find the electron inside the atom, try to find its orbital. Okay? Orbital. So if you locate the orbital, you have found the electron. So let's go ahead and see what these principal energy levels do. The first quantum number is called the principal energy level. The principal energy level was described by Bohr's model. And scientists said, yeah, there's shortcomings with Bohr's model, but we like the idea of the principal quantum number. What was that quantum number? First of all, Bohr did not call it principal quantum number. He just called it the energy level. So you had the nucleus, according to Bohr, and then you had these concentric orbits or concentric circles that made up the orbit where the electron was. And he just said, he described these orbits as having an energy level. So this is energy level 1, energy level 2, energy level 3, energy level 4. And then he said, well, when the electron is on a lower energy level, like we talked about before, the electron is very close to the nucleus, and when it's at a higher energy level, like energy level 4 here, it's really far from the nucleus, right? So scientists, it wasn't just one person who worked on the quantum mechanical model. We have many scientists working on that. So the scientists like the idea of the energy level and they brought it here, but I feel like they upgraded the name by adding the term principle. So now we don't call it energy level anymore. We call it principal energy level. For this section, it's important to recognize this. For each quantum number, you want to recognize the name of the quantum number. You want to recognize the information provided. You want to recognize the letter that goes with the name. Then you want to recognize, let's see what else besides the letter. You want to recognize the restrictions. Okay. So as we go through each one, we're kind of going over this information. Okay. Behind the scenes, we're trying to go over what's the name of the quantum number, what information is being provided, is there a letter that goes with it? Oh, I almost forgot one. And then the number, the restriction kind of goes with the number. So these are tied together. Then the number, right? Because ultimately, after going through all of this stuff here, we're just trying to get the quantum number that goes with, yeah, the quantum number, the three quantum numbers for the orbital, the last one for the electron. Okay, so back to this. Our first quantum number is called the principal energy level quantum number. This one here, like it shows, identified by the principal quantum number n. This is actually the letter, not really a number. It's identified by the symbol n. Okay, so at some point we'll come back and refer to these symbols.
Is that called like
Mathematically,
a variable?
there's a what?
Oh, isn't that called like the variable or something like that? Or
Yeah, hold on a second. Am I sharing my screen? Oh yeah, I am. Well, for right now, n is just a symbol that we use to describe the principal quantum number. Yeah, so the letter, right, versus a variable like x. It's just a letter assigned to that
okay.
term, principal quantum number, right? It's not a variable that we're going to be solving for like x or in an equation. It's just a number
Oh,
that
okay.
means right. So mathematically, there's no end to the number of principal energy levels. So this is a long way of saying the allowed values of principal quantum numbers, it technically starts from 1. The lowest value of n is 1, and it goes all the way to infinity. In my earlier class, I said infinity and beyond, right? So it starts from 1, 2, 3, 4, 5, 6, 7, all the way to infinity. Seventh level is the highest occupied by ground state electrons in known elements. So this is another way of saying of the elements we know, the highest level that we can really account for is n is equal to 7. In other words, we know there's n equal to 1, n is 2, n is 3, n is 4, n is 5, n is 6, n is 7. We know the others exist, but of the elements that we know of, we haven't really been able to verify the others exist. So for the elements we know, the very few elements that we know of that exist, we've only been able to study these levels here at the ground state. Okay? So that's what's saying right there. So then we move on, it says here, now we're going to be looking at something called the sublevel. Before we move into the sublevel, what I want to do right here is to use the periodic table. I thought I had it in this, but I'm realizing I have it in my 1411, because I forgot I had it in my old 1405 PowerPoint slides, but I switched my PowerPoint slides. So these ones don't have it. Let me go ahead and detour a little bit. Let me see if I can Google. I use this for my first class today. I'll use it later on. Right now, I'm trying to find the periodic table, not with the sublevels yet. We're not doing sublevels. Right now, I want to do energy level. So a periodic table with the energy level. So this is how the magic happens behind the scenes. I'm trying to find just the energy level. Let me see if this one will work. Not good. It's hard to find quality material on the internet. There's a lot of material, but it's not quality. Oh, come on. Okay, well, I'm not seeing what I'm looking for, so I'll just use the sublevel one I used earlier. For this sublevel one, it's showing me more than what I want. I don't want the sublevel, I just want the energy level. But we'll use this because this is all I have right now. So in this energy level, let's see, where is it? Okay, hold on a second. I actually was able to copy it here earlier today. There it is. I'll just copy it. This is the life of an instructor. One has to be innovative and think outside the box at any time. Okay, so I'm going to just add this to our slide so we can look at it. Yeah, before we go into sub-levels, I want to go ahead and add it here so I can draw all over it. It makes it easier for me. I'm going to add the page. Okay, paste the image, move this over, make this larger. And hopefully you can see this better here. So once this is on here, I can actually write on it. Okay, so this table is technically showing us the sub-level. I just wanted the energy level, but we're going to focus on the numbers only. For right now, we're learning just the principal energy level. And they're showing that to us, but they're showing us the next level also. So we're focusing only on the numbers. So let me try to make this big. as I'm writing here. Maybe not that big, this big here. So, for the purposes of quantum number, let's make helium next to hydrogen, okay? So you can see here, oh, I may have made this a little bit too big. You can see here that from this level here, if helium is here, N is 1, so I'm going to go vertically. N is 1, N is 2, N is 3, N is 4, N is 5, N is 6, N is 7. So if you're wondering what I'm doing, I'm just showing you how to use the periodic table to figure out the energy values of the elements based on their location. Okay? So before I continue this, I need to just make a disclaimer. 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 Okay? Before we continue this, the element, any element you're working on, is located in the periodic table okay the element is located in the periodic table where the last electron is located in the atom, so to say. Okay, so what I mean by that is when we think about the elements being in the periodic table, we understand that the scientist called Mendeleev placed these elements, right? He was trying to put them in the periodic table based on their similarities and their differences. But there was something else scientists noticed, that except for hydrogen, other elements have many electrons. When we are done getting all our quantum numbers, we'll be able to use the periodic table to figure out the location of electrons. Okay? So we'll use the periodic table to accomplish that goal. Where are the electrons located? And technically, we're really finding the location of the orbitals. So the location of the last electron equal the location of the element. Okay? So as I'm going through and specifying energy level 1, 2, 3, 4, this is my goal. Ultimately, I'm trying to figure out where is the electron. The 4 quantum numbers, actually the first 3, will help me figure out where the electrons are. Then once I know that, I remember where the element is located equal the location of the last electron. Once again, that's why we're using time to go over this information. You require a little bit more time, so I'm going to start this week, and then whatever we don't get done with, we'll do next week. We'll have a lot of practice before your next exam, right? So back to the periodic table. You need to know how to assign the n values. I went through the green section, right? And it's 1, 2, 3, 4. So please notice, the green section here starts at n equal 1, okay? Then the orange section, since it starts a step lower, starts as n equal 2. So we have n is 2, n is 3, n is 4, n is 5, n is 6, n is 7. So remember what this n means, right? N is telling you the energy level where the electron is. The smaller the n, the closer the electron is to the nucleus. Okay? So for whatever reason, P already starts off behind. There is no P at n is equal to 1. N is equal to 1 only exists in the green block or the S block. Down here, we start from n is equal to 3. So this is even starting a step back. N is 3, n is 4, n is 5, n is 6. Okay? This part here technically fits somewhere in here. It's kind of complicated. But look, The purple block starts with N is 4, N is 5. So my students in the morning class said this was like playing, is it Warfield, Minefield, some game that I don't play. It's like, oh, it's like playing that game. And I'm like, oh, okay. I'm not very good at playing those kind of games. Okay. But he said it was like that. Anyway, remember, the green block starts as N is 1. And then after you go over each row, from one row to another, add 1, 1, 1 until you get to N is 7. The orange block starts at N is 2. Add 1 until you get to N is 7. The blue block starts at N is 3. Add 1 until you get to N is 6. The purple block starts at N is 4. Add 1 until you get to N is 5. And that's pretty much it for all our N's. Okay? So, if you're wondering what's going on, at some point, let me just fast forward to the purpose of all of this. At some point, I will ask you, list the N value. We'll learn the the N value, the L value, the M sub L value, and the M sub S value for different elements. So right now, I'm just focusing on the N value. So to do a quick recap, I'm going to throw in some elements in here. Let me find my periodic table because you can hear it. That's my periodic table right there. Let me pull it out. Let's practice how to find our N, okay? Principal quantum number. This area is kind of crowded, so I'm gonna do it right here. Let's find silver. I like silver. I like platinum too. Apparently platinum is a thing now, so okay. Let me get me some platinum down here. PT. And then we'll do some scandium right here, SC. Then we'll do, can we do bromine? I just like bromine. Bromine. And then silicon, because you know silicon is in right now. Silicon right there. Let's do some boron. Boron right there. Okay. So, do I remember where I have my elements? No. Let me highlight them so I can see them easier. Right here. The green block is too crowded, so I won't even mess with that. You can't even see that. It's okay. Right there. Okay. So, for the elements labeled, let's go ahead and assign the N value. As we build up on this, you see how it works out. So all we're doing right now is assigning the N values. Let's see. I got scandium, CSC. I got silver, AG. I got platinum, PT. I got boron, and I got bromine. Oh, silicon and bromine. And all we're doing right now is practicing assigning the N value. Okay? So what do you suspect the N value for SC is?
Okay. Let's see. 4.
Based on this row, right? See, it's in the block. I'm missing the block. It's in the blue block.
Oh, 3. Oh, okay. Yeah, sorry.
Right. I'm sorry. I put the
That's
yellow that
my
made it look
bad.
like green. It's
That's
supposed
my
to be
bad.
3,
3.
right? 3.
Yeah.
Okay. Yes. What about AG? I think adding the yellow wasn't a smart idea on my part.
Okay, no,
What is
that
it?
one's 4. Okay.
That one is 4. Yes. What about PT? Oh, I should
Okay.
put it lower, huh? My bad.
Is that
I wrote it
6?
between.
Or
No, that this is. See, I'm getting confused with the darker lines. PT is actually up. This is my bad. This is just straight up me. Yeah, PT is right here. For some reason, I was getting side thrown off by the darker lines. Yeah, what's PT?
oh, okay, so that one's 5. Okay.
Yeah, it's 5. And then B, boron, right here.
Okay, that one should be up there. Yeah, 2.
2, right. Very good. So you're looking exactly where I wanted you to look. What about SI?
Okay, that one's 3.
3. And then BR?
Is sorry, 5.
5, right. My bad. I know my handwriting is like, what is that? Okay, yeah. So we're kind of a quarter way down. We have our first quantum number in the bag. Woohoo! And remember, this communicates the energy level of the electron. So that means that before we go into all details, the last electron in scandium is an energy level 3. Last electron. So this is the position of the last electron in the element. So different elements will have different electrons, right? So the last electron in scandium is an energy level 3. The last electron in silver is an energy level 4. You have platinum energy level 5, boron energy level 2, silicon energy level 3, and then bromine energy level 5. Okay? That's the first one. The second one, so I'm going to come back to this slide again because I need that for the second one. The next thing we learn after learning energy level is sublevel. So energy level splits into sublevels. So when you add the sublevel, you get the energy level. So the idea here is that the levels inferring, talking about the energy level, into which principal energy levels are divided are specified as the S, P, D, and F sublevel. So now we see the blocks. These
Okay.
sublevels right here, right? Now we can talk about colors, right? And I like to call these blocks, like neighborhood blocks. So now I can refer to the S, the P, the D, and the F. Instead of calling them by the colors, I can call them by the sublevels. So not only do we have energy levels, but energy levels are kind of broken apart, kind of like a subdivision. That's like describing a neighborhood, right? Oh, I'm in a different subdivision. I'm like, of what division? Anyway, people use the term subdivision without the division. So in chemistry, you have the sublevel, meaning that it's kind of it's under that level. So within the energy level, you have the sublevel. The sublevels we have here are these 4 blocks. Now, is there only 4 blocks in the world? No, there's more than 4 blocks. But at this level, all we do is discuss the 4 blocks. You have the S block, you have the P block, you have the D block, you have the F block. So the sublevel S, P, D, F sublevels, we can use the periodic table to figure out which ones they are. The sublevel, a specific sublevel, is identified by both the principal quantum number and the sublevel. So I'm going to stick with the terminology your book uses, which is a sublevel. So your book uses P sublevel or P block. In a third principal number, so a P sublevel in the third principal energy level is the 3P sublevel. When you're writing the sublevel, there are 2 ways to write it. You write it in the N and the L. So what I'm going to do here in describing this part, because they did a so-so job with this part here. Technically, there's a second quantum number that's called the azimuthal quantum number. And when you combine the first and the second, that's when you really get the sublevel. So I'm going to talk about this because it makes more sense. Okay? In the sublevel, you're comparing or you're combining the first quantum number N and the second quantum number that has the symbol L. For the N, you have to write that as a number. For the L, you will write this as a letter. And the options for the L is, with L, you have S, P, D, F. And you saw how we had S, P, D, F in the periodic table. S is always written first, then P comes second, then D comes third, then finally we have F. So over here, we're gonna combine 2 things, and that's how we get this. Oh, let me see. So over here, we're gonna have, let's see, we know it's N is 1, but it's S block. So everything in here is gonna be S block. So we're gonna have 1S, 1S, 2S, as you can see, 3S. Combining the energy level with the sublevel, 4S, 5S, 6S, 7S. Okay? And then remember, this 1S belongs with the rest of this, the green section. The P block starts at 2. There is no P block in the first energy level. So we start with 2. 2P, 3P, 4P, 5P, 6P, 7P. And how far out does P extend? Since this whole block is P, we're essentially looking at a row, right? This first row here in the P block is 2P, second row 3P, third row 4P, That one 5p, 6p. Over here in the S block, first row 1s, 2s, 3s, 4s, 5s, 6s. So you have that whole area in the block belonging to that sublevel. In the D block, you have this whole area here. From here to here, starts at 3D. Then we get to 4D, from there to there. Then we got 5D, from here to here. Then we got 6D, from here all the way to there. That's the D block, right? Like the subdivision, D block, sublevel. Then we finally have the F block. With the F block, we have, remember, the S starts from 1, the P starts from 2, the D starts from 3, the F starts from 4. So we have 4F being the lowest and then 5F being the next level. So from here, you can see the block being referred to as a letter, the energy level as a number. Oops, 4F, 5F. I'm going to get this right. There. Okay? So yeah, now we got the energy level, we got the next number. Well, we got it in a letter form. So the number of sublevel with the principal energy level is equal to n. So what they mean by here, let's do some consolidation. Let's do some, okay? It doesn't, what they're talking about here doesn't always work. Based on the ones we know, it sort of works. Let's look at energy level. Energy level versus the sub level. For energy level 1, we only have one sub level, 1s. Energy level 2, so I'm going through and finding out, for energy level 1, I only have 1s, right? Because there's no 1 here in the P, or the D, or the S, or the F. There's only energy level 1 in the S block. Energy level 2, on the other hand, can I find a different color? Maybe like dark pink or something? Let me find dark pink. Because it's hard to find it. Let me use purple maybe. Energy level 2, I'm going to highlight all the energy level 2. This one here is energy level 2. This is energy level 2. That's it. D starts at 3. F starts at 4. So for energy level 2, I have 2. I have 2S and I have 2P, right? You saw that right here. 2S and then 2P. Let's find all the energy level 3 sublevels. Energy level 3 sublevel. Let me use a different color. Does it make a difference? Now let me try blue. Energy level 3 sublevel is this one here. Why is it not allowing me to write? Is this one here. That one is 3S, 3P, 3D. There's no 3 in the F, so you can see. In energy level 3, there is 3 sublevel. 3S, 3P, 3D. Okay? And then we have energy level 4. Let's find all the ones that have energy level 4 and the number 4 before the letters in the blocks, right? You can see right here. There's energy level 4 there. 4S, 4P, 4D, 4F. So we have 4 of these. 4S, 4P, 4D, 4F. Okay? So what they're saying there is if you know the energy level, you can figure out what the sublevels are or how many different sublevels they are. Okay, there's only one type of sublevel for the S, and it's 1S. There's 2 of the energy level 2, 2S, 2P. 3 of the energy level 3, 3S, 3P, 3D. 4 of energy level 4, 4S, 4P, 4D, 4F. Okay, I hope I said that right. Yeah, there's 4 of these. 1 of that, 2 of that, 3 of these, 4 of that. Okay, so there is a connection between them. Any questions? So then they make this statement based on that relationship. Number of sublevels within the principal energy level is equal to the n. Okay, and we're just going to energy level 4 based on this right here. So of course, we're told for the sublevel, for elements other than hydrogen, the energy of each principal energy level spreads over a range related to the sublevels. So we're told here, as we're looking at these sublevels, please recognize, so this is what I showed you before, right? When n is equal to 1, oops, what did I do to the pencil? Hold on. When n is equal to 1, hold on. Oh no, my pencil. You know what? I forgot to charge my pencil. Give me just a moment. Oh no. I'm trying to see if it's dead or if it's just. Oh no, no, it's not dead. Woof! That was close. That was a close one. So energy level equal 1, we have 1s. Energy level equal 2, we have 2s, 2p. So we're being told here, just notice that as far as the energy level is concerned, or the sublevels, s has lower energy than p has lower energy than d has lower energy than f. So that between these two, s is lower energy than p. So 2s would be lower in energy than 2p. Then for energy level 3, 3s will be lower in energy than 3p, which will be lower in energy than 3d. Okay, so I'm just going over this. Then for n is equal to 4, what we see is 4s is lower in energy than 4p, which is lower in energy than 4d,
Okay. Oh, okay.
which is lower in energy than 4f. Yes. Do you have a question?
No, no. Okay, I'm good. Thank you.
You sure?
I forgot to read the SPDF part. Not gonna lie.
Yeah, yeah. The s comes before the p, before the d, and before the f.
Okay.
Right. So yeah, they're showing you this. And then they're showing you this right here. So when you arrange them in order, you see these are all the energy levels here. And if you're going up, you're increasing. So the bottom here, you have lower energy. On the top here, you have higher energy. So what they're showing you is if you were to take the sub levels for energy level 3 and energy level 4 and you arrange them, that's how it will be. So within the same energy level, you see all of these are energy level 3, N is equal to 3, S is lower than P, which is lower than D, right? These are all, I'll show you right here. These are all N is 3, same energy level. Within the N is 4, same energy level. When N is equal to 4, we get to 4S first, before 4P, before 4D, before 4F. But
Okay.
when you're in the atom and there are many electrons and stuff, these are not as separated like that. The 4S, if you look at this, if you're comparing as far as the energy level is concerned, since this part here is lower energy and the top part here is higher energy, let me show you where I'm focusing on right now. This part in the middle. It looks like 3P has lower energy than 4S, right?
Yeah.
And 3D has higher energy than 4S, correct? And you
Yeah.
can also say 4S has lower energy than 3D, right?
Yeah.
So yeah, I'm looking at this picture here and making my conclusion based on this picture. Yeah, anything that's lower or on the bottom is lower energy. Anything that's further up is higher energy. So yeah, so somehow 4S has a lower energy than 3D, even though if you compare all the energies of 4 or everything that has the energy level of 4 within the like groups, 4S is lower than 4P and 4D and 4F. If you were to compare all the three energy level 3S is lower than 3P than 3D. But when you start to layer them all together, 4s finds itself between these two. So if that seems so complex, let me show you an easier way to understand that. Go ahead and look at the periodic table. As far as energy is concerned, let me go ahead and erase all the stuff I wrote here. The way the sub-levels are written in the periodic table, it works out so that the sub-levels are written from the lowest energy level. So I'll say here, lowest energy level to, let me say, the highest. It's not really that simple. Just the lowest energy level is the one on the left. And we read from left to right. So you start with this level right here. This is the lowest level. 1s will be lower in energy than what comes next, 2s. Because don't forget, this green piece over here technically fits right here to complete that puzzle. Then 1s comes before 2s. 2s, from 2s, go from left to right, go to this, comes before 2p. After 2p, go back left, 3s, right here. After 3s, go to the right, we have 3p. You see, after 3p, we didn't go to 4s. I mean, we didn't go to 3D, we went to 4s first, because remember, 4s was the one that was kind of coming in between 3p
And 3D.
and 3D. Right. So I'm glad you remember that. So then 4s comes next, and then 3D. So when you go from left to right in the periodic table, you get the right order. Okay. We're going to be
Oh,
doing that later on when we deal with electronic configurations. Did you
okay.
ha- did you have a question?
Oh, I was just thinking like the fact that like I feel like it was related to the fact that like how I remember it. How on the left side of the periodic table it's like that's where it has almost no remaining like one or two remaining electrons
Oh, valence
in the outer
electrons?
shell versus at the very
Right.
end like it's
Right.
completely filled like the last shell whatever.
Yes, yes. It does relate to that, and this is the foundation that leads to that idea. Right.
Okay.
Yes. So let me see. Let me see. Where are we? We're right here. So we're done with that. So then finally, we had our first quantum number. Now we're looking at the next quantum number right here. This is the electron orbital. So over here, they don't go into all the details that we do in general chemistry. Even though I'm tempted, I have to remind myself that in you guys' level, when we go over the N, the L, the M sub L, then finally the M sub S. We may not even go into this one here. The N for you guys is written as a number. So right here, number. The L is written as a letter. And then here, we don't even describe the actual numbers. We just give an amount like they give you over here. And then we talk about this too. So we kind of approach it not in details, but in a way that forces you to memorize. Okay, so I don't want to go
Oh,
into all the stuff that we do in general chemistry. I'll just give you guys an easy way to figure this out without doing general chemistry. So we're done with the first principal quantum number. The next one here I mentioned, this is going to be for you guys the sub level, which we did that part two. Next one will be orbital level. In the orbital level, which is the level right here, we're not describing each individual quantum number, but we're looking at it holistically. So the one thing that they didn't actually mention in the sub-level, no pun intended there, the sub-level actually provides you the generic shape of the orbital. So let me go back and fill in that gap because I just realized by me sticking with this, they're kind of leaving out some certain information. Okay, so let's compare Bohr versus quantum mechanical model. Bohr talked about electrons living in orbits or being found on orbits. And these orbits were essentially concentric circles, a circle within a circle within a circle, kind of like a Russian doll. And you had the electrons on these very prescribed orbits. The electrons were like particles We got the idea. And then now you have the quantum mechanical model where you have these different shapes for the sublevel. And the sublevel gives you generic shape. The generic shape we have now is not just round, but we have S, P, D, and F. S, P, D, and F not only describe the sublevel, they also describe the generic shape of the orbitals in those sublevels. So back to that whole analogy I was giving you guys earlier about the neighborhood and the block. The orbitals that we'll talk about in a second or in a minute, the orbitals that exist in the S block or the green block are all spherical. And so I'm going to show it to you right here. So the S block orbitals are actually spherical. These are round, but a sphere. The P block orbitals are figure 8, also called the dumbbell. It looks like two spheres tucked together. The D block orbitals are a clover leaf, which look more like four circles stuck together. Okay, I'm not the best artist at all. Do you know I thought I used to be a very good artist? Okay, and then the F block, the F sublevel orbitals are made up, most of them are made up of 8 circles, which is kind of like doubling, right? From here to here, we're doubling and doubling. 8 circles, but they end up looking like a flower. 1, 2, 3, 4, 5, 6, 7, 8. So it ends up looking like a flower. So I used to just call it the flower. Okay? We'll just call it the flower. If they can name the other ones what they are, we can call this the flower. Okay? 1 circle, 2 circles, 4 circles, and then the flower. Now recognize that not all the D block orbitals have this shape, but a majority, this is the most common shape.
Okay.
And then the same thing with the F block, this is the most common. So what we are seeing, that's why I call it the general shape. What we are seeing here for the sublevel is the common shape. So when they get to the orbital part, we have to have this communicated before we can even get to the orbital part, because in the orbital part, we'll see the specific shapes. Okay. Okay, let me scroll down. Oh, yeah. So now we can say, what are these orbitals? Orbitals is an improvement on what Bohr came up with. I just feel like when these people are coming up with this model, they're trying to almost one up what Bohr said. He came up with orbits. They're like, we're gonna do orbital. He came up with energy level. They said we will do principal energy level. Okay, just one up. Mathematically, these orbitals are probability maps. Probability maps. It's a map, really. It's more like a 3D map. It's a map that gives you the probability of finding the electron. So, mathematically describe a region in space around the nucleus. So the context here is inside the atom around the nucleus. There is a 3D region in space around the nucleus in which there is a high probability of finding an electron. Okay? So each sublevel has a certain number of orbitals that is increasing progression, that is an increasing progression of odd numbers. So we're being told for the S orbital, we only have, for the S sublevel, we only have 1 orbital. For the P sublevel, we have 3 orbitals. For the D sublevel, we have 5. For the F sublevel, we have 7. Okay? So remember how I was drawing all of this before? I'm going to add this to you again so we can see. So we had the energy level. Now we're looking at the sublevel. The sublevel and the number of orbitals. So for the sublevel S, we only have 1 type of orbital. For the sublevel P, we have three types of orbitals. I'll show you guys the picture so you can make the mental connection between the two if you're a visual learner. For the sublevel D, we have five types of orbital. For the sublevel F, we have seven types of orbital. So let me see. I'm trying to think in this. Oh, there it is. Yeah, here it is. Finally, this is the actual shapes of the orbitals. What is missing here is F, but that's okay. We have S right here. We have P. We have D. Okay, so S is spherical. You can see right here, and they're showing you the shape based on the axes, right? You can see the
Yeah.
X, you can see the Y. Chemists like to make Z vertical. Oh well, we'll just go with what they're saying. Z is vertical.
Believe it or not, that actually works also in 3D modeling programs too.
Really? We never
Yeah.
did that in math. I never did 3D modeling. So we never did that in math, and I'm like, what is this? Why is Z vertical? What happened to in and out for Z?
Yeah. How they try to remember it or how to memorize it is they'll say imagine X and Y being part of a map and like laying it across like a table and then
Mm-hmm.
Z is up and down as if like you're looking at the picture.
Right.
Yeah.
Yeah, thank you for that. I had to learn that when I was in middle school. I wasn't very happy with learning something new when we have it already established in math. I just said chemistry people are always trying to invent the wheel to reinvent it, but I got over it.
Oh yeah.
So yeah, I'm glad you know the Z is vertical. So we only have one variation of the s orbital. That's it. Sphere. It can't get any more rounder than that. That's the sphere. Okay? But when it comes to the p orbital, that is actually figure 8 or dumbbell. The variations are just the orientation according to the axes. So this one here is called px. It is a p, but it's called px because the orientation lines up with the x-axis. It looks like the x-axis is poking right through the p orbital. Okay? Then you have py, where you have the y-axis poking right through the p orbital, so it's called py. Same type of orbital, same shape, different orientation. For that reason, these are considered to be different. And then we finally have pz. Pz, you have the z-axis poking right through the orbital. Okay?
Okay.
So these produce the three different orientations of the p's. With S, no matter how you orient it around the X, Y, and Z axis, you get the same thing. Therefore, we only have one. We don't have variations of S. When it comes to D, remember D was the one that had the four circles or the clover leaf shape?
Over.
Of
Yeah.
course, we have this one here. So we have one, two, three, four. You pretty much have the four circles, right? And they're oriented differently. Now, you guys, at you guys' level, this being a non-majors class, you want to recognize, hey, this is a D orbital, D, D, D. But you won't be asked, you know what, I shouldn't make promises. I don't think, that's my disclaimer, that you will be asked to necessarily identify these ones here. This last one, though, is so unique from the other four, they tend to ask questions about that because it looks like a p orbital with a floaty, right? In the
Yeah.
equatorial region, right? When you see the F orbital has one of these two with two floaties. I'm like, what? What is this? Pass one around for every level except for S? But yeah, in the F sublevel that looks like a flower, you have what looks like a p orbital with two floaties. So I'm like, yeah, that's interesting. Anyway, these bubble looking things are essentially the region, if the nucleus is somewhere in here, the region around the nucleus where there's a very high chance of finding the electrons. That's the purpose. So imagine, right? In Bohr's model, his orbits were all round. So we believe he only saw the s orbital, but his technology didn't allow him to even see the s was 3D. So he saw the S over and over and over and over again, but the different sizes of the S. He never saw them as 3D, or he never saw these other levels. So he wasn't wrong. His model was just incomplete. Okay.
Okay.
Yeah. I mean, there's some books that just flat outright say he's wrong, but you know. So so
Yeah,
here's
just where
the
that perspective changes everything.
right. So here's the difference between Bohr's model and the quantum model. In Bohr's model, you see the electrons here as particles, right? They look prominent. Look at their size compared to the nucleus. Look at their orbit as they're orbiting around the nucleus. And they have a very prescribed path. And you can almost predict where the electron is going based on its orbit. Here, we're looking at a probability map. It's hard to see the dots, but every single dot here represents a part where the electron was once seen. Imagine the software that was designed to record this. And before they had the software, imagine somebody sitting there and they're writing this down. Dot 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 dot. So they kind of record all the little specks. Then in the end they say, the specks make a shape that looks like a circle. It's gonna be round. 3D. There it is. And the nucleus is somewhere here in the middle. Dot 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 dot. So all these little specks represent a location where the electron was once seen, maybe even for a fraction of a second. And eventually it makes a circle. Okay? And that will essentially be your s orbital. Yeah. So that's kind of compare and contrast, right? This one here is more certain, more sure about the electron location. Here we're like, we know the region, the area ish, right, where the electron is. Okay, so like we said, they're different sizes from this for the same orbital. You have energy level 1 here. You can see that the labels 1s, 2s, 3s. So all this is saying the s at the energy level 1 is smaller compared to the s orbital at energy level 2. Because remember, these are all in the same atom. So you would have a nucleus. If we are only showing the s orbitals, you will have the nucleus. You have the first energy level, n is 1, but not a circle, but a sphere. Second energy level, n is 2. So it kind of looks like what Bohr was showing, but this is actually 3D. Third energy level, n is 3. Okay. So of course, when you technically see n is 3, inside n is 3, you will see n is 2. Inside n is 2, you will see n is 1. And then inside n is 1, you see the nucleus. Right there. Nucleus. Then here you see n is 2. N is 2. Okay, they're only showing you the outer layer versus the inside.
Okay.
Okay. So I'm trying to see how far I want to go. Yeah, we'll go all the way to we'll go all the way to right before electronic configuration. So we'll do electronic configuration when we meet next time. So that way I can imagine what I'm saying right now is already overwhelming. I don't wanna overwhelm. Overly teach, overly present. So looking at this judgment right here, we don't actually study the last quantum number, the magnetic spin, but I'm going to tell you about it anyways, because in a way, in a backhand way, we talk about it using the Pauli's exclusion principle. Okay? Magnetic spin is the fourth quantum number that describes the electron in the orbital. So remember, the first three quantum numbers, the first three quantum numbers, that will be the energy level, the azimuthal. Oh, I didn't tell you what the last one was. I'll give you the actual name. It's called the uh angular. Sorry, the magnetic. Oh my goodness, now I'm blanking out. Magnetic. The second one is called azimuthal and angular. Same thing for the second one. Magnetic for the third, and then finally spin. So these are the actual names of the quantum number. The energy one is called the principal. So these are the actual names for real. Principal quantum number, angular momentum quantum number, magnetic quantum number, spin quantum number. These are the names of the four quantum numbers. Now you guys don't necessarily have to memorize those names. Just be aware of it. For the first one, which you guys call the energy level, they're giving you guys the kind of the more casual terms for these. So energy level for you guys is what we will call the energy level for you guys is what we will call the principal quantum number in the majors class. What you guys call the sub level is what we will call the azimuthal quantum number. And then what you call the orbit is what we will call the magnetic quantum number. And then finally, there isn't actually a name for this last one, but we call it the spin quantum number. So for the spin quantum number, please notice for this one here, the spin has two possible values, plus 1/2 and negative 1/2. So what this means is the orbital, the different shapes we saw back here, each of these shapes can either be completely empty. So you can have a portal or a pod of any of these shapes inside the atom that's empty. Okay, so these are the orbitals. There are three possible states. You can have, for the orbitals, let me write this down. For the orbitals, you can have a completely empty orbital. You can have one that's half filled, which is one electron, or finally full filled, which is two electrons. So the orbital can be empty completely. That's one possibility. It can just have one electron, or it can be full with two electrons. But Pauli's exclusion principle is the principle that scientists came up with based on their observation and their findings in the experiments. They noticed that when electrons were orbital mates, that's what I call them, or roommates, when you had electrons in the same orbital, they had opposite spins. Okay? So this rule was then made because they kept seeing that if you had an orbital that was doubly occupied by two electrons, it's almost like the electrons had an agreement. One had one directional spin, the other one had the opposite. So you had clockwise and anti-clockwise. When the electron was in there by itself, if it was just one electron, they usually had the positive 1/2 spin. If there were two, one was positive 1/2, the other one was negative 1/2. So this implies or indicates opposite spin. So now we're going back to Pauli's exclusion principle, where he says, limit the population of any orbital to two electrons. The electrons, if they're going to be in the orbital, max is two. That's it. The orbital, like he says, may be unoccupied, empty, occupied by one electron, or occupied by two electrons. There is no other occupancy arrangement that's possible. Only these arrangements are possible. Okay? Only those variations are possible. So before I even look at the electronic configuration, let me go over this part real quick and then we'll resume next time. So let's assume these orbitals here are maxed out and each one has got a maximum of two electrons. The way they draw these later on is they use half arrows to indicate positive spin and negative spin. So this is one electron, this is the other, roommate. Up, down, roommate. Or you can put them next to each other. Up, down, up, down, up, down. So I'm showing you electrons that are occupying the same orbital and they have opposite spins. So that was actually Pauli's rule. Pauli's like, yeah, you can have two electrons. The orbital can also be empty. But if you have two electrons, they have to have opposite spins. It's not negotiable. That's it. Okay? And so let's see. from here on, we're dealing with configuration. So I want to start this. I was going to do this part and this part today, but I realized it's configuration. I would like to start with configurations next week so we can have a complete thought in the same place. Okay? So we talked about the quantum numbers today, and then next week we will continue with this section here, configurations, and then you have your exam. When is your next exam? On Sunday?
Let me double check. I'm checking correspondence.
I want to say it's on Sunday. Listen, I don't. When I go from one class,
It's 10/18. So
okay.
yeah, so it looks like it's next week or whatever time 10/18 is. I'm not very good with
Really,
calendar.
10/18? That's what I. Oh, this is the wrong class.
That's okay. Yeah, so that's
You know what? Okay, what I'm gonna do, I'm gonna finish this chapter next week, and then I'm gonna continue. I'm not gonna wait because, yeah, as time, you guys can always do your exam earlier. Towards the second half of the semester, people start getting really tired, and that's when they start falling behind. So I'm just gonna keep going on. But yeah, next week I'm gonna finish this chapter. I mean, of course, if you guys want to take a break, I will do that. It won't make a difference for me. But I would rather finish this chapter so that if you guys want a break to do the exam, I can also do that too, and then just continue with the exam. But as far as this is concerned, I will be finishing this chapter next week, and then at that point, I'll ask the ones that show up what you want to do, and then I can continue the next chapter. If you feel like it'd be too much to learn a new chapter and the old stuff, I can always give you some time off to take your exam, and then we'll continue when the exam is over. Okay? But this will be decided next week.
Okay.
Yeah. Other than that, what you
and if
say?
it's just me, I'll assume that they'll want extra time. Like that's like people in general.
Yeah. That's what we did last time, and I lost half the class. I mean, they're still enrolled, but just stopped showing up. I'm like, wait, what happened? So I don't know about doing such things, but no, that's okay. Yeah, we will finish this next week, and then you guys will have time to prepare for your exam.
Gotcha.
Okay.
Okay.
You have a nice weekend.
I hope you do too. See you Tuesday.
Okay. Thank you. Bye. Wait, where's the
Okay.
stop button?